Okay, hi everyone. So welcome back. So today will be the third video on Faraday's law, and in this video we're going to study how to change the magnetic flux by changing the orientation of the coil. So when we say we change the orientation, right, it means like if this is the original orientation of the coil, we might need to rotate it this way, or we might need to rotate it this way in order to change the angle of the area vector with respect to the magnetic field. So the magnetic field might be pointing into the page, and we put our area vector to be pointing downward as well. But if you rotate, then the magnetic field will still remain at the same direction, but our area vector will change direction. So the angle between the magnetic field and the area vector will change if we rotate the coil. And this is what we are going to study, as changing a theta is going to change the magnetic flux through the loop over here. Okay, so let's look at example 17.16. So we have a coil with 150 turns with an area of 36 cm square. So it's being stated here, I have drawn a circular coil to represent the situation. And this coil here has 150 turns with an area of 36 times 10 to the power negative 4 meters squared. And this coil here is rotating in a uniform magnetic field. So I draw all these crosses to represent the uniform magnetic field. They didn't define for me where is the magnetic field pointing towards, so I just assume it to be pointing into the page. That's why it's easier to draw and it's easier for you to see as well. Okay, then it tells that the magnetic field is 0.24 Tesla. So this is what I've written down over here. Okay, the axis of rotation is perpendicular to the field. So I've drawn my axis of rotation to be this line over here, and it is perpendicular to the magnetic field over here. The magnetic field is pointing into the page, but the line is on the plane of the page. So it's perpendicular. One is into the page, one is on the plane. So the angle between them is 90 degrees. Okay, and the coil is rotating at 20 hertz. When they say 20 hertz means that 20 per second. So for every second that has passed, this coil here will undergo 20 complete complete rotation. Okay, every second has passed, the coil here will undergo 20 complete rotation. That's the meaning of 20 hertz. Okay, so for this diagram here, it's just from my imagination. There are things that they didn't define clearly, and I just simply assume a direction. Like the direction of the magnetic field, whether it's pointing into the page or out of the page, to the left or to the right, up or down, that is not mentioned. The circular coil, whether it's oriented on the plane or it's oriented perpendicular to the plane of a page, they also didn't tell, so I just simply assume a direction. The axis of rotation, they do tell that it must be perpendicular to the magnetic field, but perpendicular to the magnetic field can be horizontal, can be vertical, can be at an angle. Even if you draw your axis of rotation to be at an angle, you can still see that the axis of rotation is perpendicular to the field. So all this, I just assume the direction in order for me to understand the situation better. As long as you fulfill all the requirements mentioned in the question, you should be fine. Okay, so after that, they ask you to determine the maximum induced EMF and to ask you to determine the induced EMF when the coil makes an angle of 35 degrees with the field line. So we're going to investigate this thing over here using Faraday's law as usual. So Faraday's law tells you that the induced EMF is the negative of the time rate of change of the magnetic flux. So in this case, it's magnetic flux linkage because there's more than one turn. So the magnetic flux linkage, we can expand it to become NBA cos theta. BA cos theta is the magnetic flux, multiplied by N, you get the magnetic flux linkage. So over here, let's see what has changed, what has not changed. The number of turns over here, even though you rotate the coil, the number of turns on the coil will still be 150 turns. You won't suddenly lose turns, you won't suddenly gain turns just by rotating the coil. So the N is constant, you can bring it out from differentiation bracket. Next, the magnetic field. The magnetic field, they didn't mention you change the magnetic field in any sense. It's still remaining at 0.24 Tesla. In that case, you can bring out the magnetic field out here. Next, the area is 60 cm square. You are rotating the coil. Rotating the coil does not cause the area to change. So you can keep the area as the original area, 36 times 10 to the power negative 4 meters square. What's changing here is the angle between the magnetic field and the area vector. So in this diagram over here, we take the magnetic field to be pointing into the page. So we will also take the area vector to be pointing into the page as well. So right now, in this particular diagram over here, the area vector and the magnetic field has an angle of 0 degree between them. The magnetic field is pointing into the page. The area vector is also pointing into the page. The angle between them is 0 right now. But if you rotate the coil, right now, you can think of the situation like this. Uh, this is the area vector and the magnetic field. But as you rotate to an angle, the magnetic field is still pointing into the page. That is still fixed. That is still fixed. But your area vector has changed because it follows the rotation. It must be perpendicular to the board, but the magnetic field still remains the same. So initially it's like this, but once you rotate, the area vector will follow because it must be perpendicular, but the magnetic field will stay. So the angle between B and A will change due to the rotation. Okay, so because of that issue, the data will change. So we are going to keep the data inside here. Okay, so how does the data change? Well, we say that this is rotating at 20 hertz, right? So they already tell you the frequency of the rotation already. So you can express the data here in terms of omega t. Okay, you can express the data in terms of omega t because as time passes, they will rotate greater and greater angle, right? So you take omega, the angular frequency, times the amount of time that has passed, then you are able to get back to the data that you want to fit in right now. Okay, you change the data to become omega t. So right now, this is cos omega t, differentiate against t, where it's just negative sign, cos change to negative sign, omega t remains, then you differentiate inside the bracket, you get omega outside. So if you rearrange it, the negative will cancel each other out. So your induced EMF will be MBA omega sine omega t. Okay, so in this situation here, there's no sense of direction anymore because you don't know whether it's rotating clockwise or anti-clockwise, whether it will cause angle between the B and A to increase or decrease. You can't know for sure if you just say for a general statement that it's rotating. So therefore, this equation over here won't tell you about the direction of the EMF. In fact, the direction of the EMF will change throughout the rotation. Okay, so this one will not tell you the direction. So if you look at the situation, they ask for the maximum induced EMF. Well, we have a sine omega t behind, and you learn that if it's they ask for maximum, then you should take the sine omega t to be equals to 1. Then your omega max, your EMF maximum will be MBA omega. Okay, the sine omega t, you change it to 1 because it's the maximum you can achieve when the sine omega t is equals to 1. So now you can just take MBA omega. Omega is equal to 2 pi f. Angular frequency is 2 pi times the normal frequency. So you can now do your substitution. 150, 0.24, 36 times 10 to the power negative 4, 2 pi f frequency, which is 20 hertz over here. Okay, so once you have done that, you will find that the maximum induced EMF is 16.3 volt. Okay, whether it's in the clockwise direction or anti-clockwise direction, you can't know for sure. In fact, you at every moment throughout the rotation, the direction of the induced EMF keep changing because at certain point in time, the magnetic flux is reducing if the magnetic field passing through the coil is reducing. Your coil is rotating up. Your coil, let's say this is the whole coil experiencing magnetic field, but as you rotate, you have less area experiencing the magnetic field. What you see here, the 2D shape that you see here, you can see that the shape is reducing. Then after the area increase again, then the area reduce again. So there will be a constant increase and decrease of the magnetic flux. Therefore, the induced EMF will keep on change direction throughout the rotation. So in this case, this value here doesn't carry any meaning regarding the direction because the direction of the EMF keeps changing. Okay, next thing it asks for the induced EMF when the coil makes an angle of 35 degrees with the field lines. So the coil is going to make an angle of 35 degrees with the field line, not the area vector. It's the coil that is going to make an angle of 35 degrees with the field line. So that means, but if you try to view it from a certain angle, let's try to view it, let's say you try to view it from this angle. Okay, if you view it from this angle, then this is what you will see. You will see the magnetic field line pointing downwards. Okay, so just now this is what you see. You see magnetic field pointing into the page. So now you look at it from this angle. Okay, from this angle, then you see that it's magnetic field pointing downwards. Okay, so now you see magnetic field pointing downwards, and the coil is making an angle of 35 degrees with the magnetic field lines. Okay, this is the coil, the plane of the coil. Just now you are able to see the whole coil, but now look from the side, you can only see a line that is representing the plane of the coil. So the plane of the coil makes an angle of 35 degrees with the field lines. So if you check properly, the angle between the magnetic field and the area vector is 55 degrees. So you have to be very careful when you're seeing which angle to substitute in. The plane and the magnetic field, the angle between them is 35 degrees, but the area vector and the magnetic field, the angle between them is 55 degrees. So when they say the coil makes an angle of 35 degrees with the field line, it means that the magnetic field and the area vector has an angle of 55 degrees between them. Okay, so now you are not finding the maximum EMF, you are finding an EMF at a certain angle. So you can use back the equation, this equation here, which is not for maximum case. You can use back this equation, but since they're not telling you at what time, they're just telling you the exact angle, you can change the omega t back into theta over here. So it becomes MBA omega sine theta. So now MBA omega sine theta, you can just put in everything, then you're able to get the induced EMF. Okay, at this moment, this value here also won't tell you the direction. The positive or the negative here will also not tell you the direction. Why? Because you don't know the direction of the rotation. You don't know whether the rotation is going this way or you don't know the rotation is going that way. So if you don't know whether the rotation is causing an increase of magnetic flux or a decrease of magnetic flux, if you're not able to make sure of that, then technically you cannot know the direction of the induced EMF also. Okay, if you are able to know clearly whether it's an increase of magnetic flux or decrease of magnetic flux, then you're able to determine the direction of the induced EMF. But in this case, they just tell you the angle between them is 35 degrees. They don't tell that it's rotating clockwise or anti-clockwise, this kind of thing they don't tell you. So you are unable to determine whether the magnetic flux is increasing or decreasing. Therefore, your value here, your induced EMF here, the sign carries no meaning. It's to tell you the direction of induced EMF. Okay, so I've only prepared one example for this thing because it covers two different types of situations that is commonly seen. One is to find the maximum induced EMF, which is by changing the sine omega t to be equal to 1. And another one, you might need to substitute in the angle, but you have to be very careful at looking at what's the angle to put in. Okay, so this is the third way of changing a magnetic flux, which is by changing the orientation of the coil. By rotating the coil, you are able to change the magnetic flux, and by changing a magnetic flux, you are able to induce an EMF. Okay, if you want to determine, no, nothing. Okay, so this is the way to do it. I have no more example for this particular method of changing magnetic flux. So that's all for this the method over here. So in the next video, we are going to look at Lenz's law and trying to see why do we say all those magnetic induction effects are opposing the cost of that, the cost of your induction. Okay, why the effect is opposing the cost. We'll try to look at that in the next video. So that's it for this video. Thank you very much.